Okay, so you want to own a semiconductor factory, buy some sand, melt it into silicon, print a few microscopic circuits, and sell the chips powering every phone, car, missile, data center, and artificial intelligence system on Earth. It sounds like the perfect business. Demand is exploding, governments are offering billions in subsidies, and your customers are some of the richest companies in history. But here's the strange part. A modern semiconductor factory can cost more than an aircraft carrier, become technologically obsolete before it has paid for itself, and lose money while operating at full speed because too many invisible defects appeared on a piece of silicon. By the end of this video, you will understand what it costs to build a chip factory, how manufacturers make money, why yield matters more than almost anything else, and how one machine controlled by one company in one European country became the gatekeeper to the entire AI economy. First, you need to decide what kind of factory you're building, because semiconductor factories come in three completely different categories. The cheapest is an assembly and testing facility. It does not manufacture the silicon itself. It cuts completed wafers into individual chips, packages them, connects them to tiny electrical contacts, and tests whether they work. Depending on its size and sophistication, a facility like this can cost hundreds of millions of dollars. The second category is a mature node fabrication plant. These factories manufacture chips using older processes such as 28, 40, or 65 nanometers. Older does not mean useless. Cars, washing machines, industrial robots, medical devices, power supplies, and military equipment depend on these chips. A mature node fab can still cost several billion dollars, but the equipment is cheaper, and the manufacturing process is better understood. Then there's the leading edge fab, the kind producing processors for flagship phones, advanced graphics cards, and AI systems. Building one can cost between $10 billion and more than $25 billion. And that number does not represent one giant machine. It represents thousands of tools arranged inside one of the cleanest, most precisely controlled buildings ever constructed. The building itself is almost a machine. Floors are isolated from vibration because movement too small for a person to feel can ruin a manufacturing step. Temperature and humidity are tightly controlled. Air passes through massive filtration systems because a particle smaller than a human skin cell can destroy a circuit. Workers wear full-body suits, not primarily to protect themselves from the chips, but to protect the chips from themselves. A person walking through an ordinary room releases hair, skin, dust, and moisture. Inside an advanced fab, the human body is basically a contamination event with legs. Before production begins, you also need electricity, and a lot of it. Fabrication equipment, cooling systems, vacuum pumps, air filtration, and water treatment must operate continuously. A power disturbance lasting fractions of a second can interrupt sensitive processes and damage wafers that have already spent weeks moving through the factory. This is why fabs require redundant electrical feeds, backup systems, and extremely reliable local infrastructure. Then there is water. Chip manufacturing repeatedly cleans wafers using ultrapure water that has been filtered so aggressively that it contains almost nothing except water molecules. Ordinary drinking water is nowhere near clean enough. The facility must take municipal or industrial water, remove minerals, organisms, gases, and microscopic contaminants, use it across the production line, then treat or recycle much of it afterward. You're not simply building a factory. You are building a power system, water system, chemical plant, laboratory, and precision manufacturing operation inside the same perimeter. Now comes the shopping list. A fab needs deposition tools that add microscopic layers of material, etching tools that remove selected material, ion implantation systems that alter the electrical properties of silicon, metrology equipment that measures structures almost atom by atom, and lithography machines that project circuit patterns onto the wafer. Lithography is where the numbers become ridiculous. For the most advanced chips, manufacturers use extreme ultraviolet lithography, or EUV. These machines are produced by ASML in the Netherlands. Its newest high-NA EUV systems cost more than $400 million each. One machine costs roughly as much as several wide-body passenger jets. It is not delivered in one piece. The system contains components manufactured across multiple countries, is divided into modules for transportation, and requires several cargo aircraft to ship. Inside, Droplets of molten tin are fired through a vacuum chamber and struck with lasers tens of thousands of times per second. The resulting plasma creates extreme ultraviolet light, which is then guided using some of the smoothest mirrors ever manufactured. The light prints patterns so small that conventional optical systems cannot produce them, and you do not buy one. A serious leading-edge factory needs a collection of lithography systems and hundreds of other tools surrounding them. By the time the clean room is filled, the equipment inside can be worth considerably more than the building holding it. So, where does the money come from? There are two main business models. An integrated device manufacturer designs and manufactures its own chips. Intel traditionally operated this way. Samsung also designs products while manufacturing chips. The second model is the pure play foundry. A foundry manufactures chips designed by other companies. TSMC does not need to design the next iPhone processor or AI accelerator. Apple, Nvidia, AMD, and other customers design chips, then pay TSMC to manufacture them. This separation created the fabless semiconductor industry. A fabless company can focus on architecture, software, and design, without spending tens of billions of dollars building factories. The foundry concentrates manufacturing demand from many customers into the same enormous network of facilities. That scale allows it to buy the best equipment, improve processes faster, and spread fixed costs across millions of wafers. The basic product is a circular silicon wafer, usually 300 millimeters across in advanced fabs. Hundreds of chip designs may be printed across its surface, depending on the size of each chip. The wafer passes through hundreds or even thousands of process steps over several months. Layers are deposited, patterned, etched, cleaned, measured, and repeated until billions of transistors have been constructed. But not every chip on the wafer works. This is where yield enters the business. And yield is the number that can turn the same factory from a money printer into a furnace for shareholder capital. Yield is the percentage of manufactured chips that function correctly. If a wafer contains 500 potential chips and 450 work, the yield is 90%. If only 250 work, the yield is 50%. The cost of processing the wafer barely changes. The same machines ran, the same chemicals were consumed, and the same time passed. But at 90% yield, those costs are divided across 450 saleable chips. At 50% yield, they are divided across 250. The effective manufacturing cost of every good chip rises sharply. Large chips are especially dangerous because they occupy more wafer area and have a greater chance of intersecting a defect. A small controller may allow thousands of units to fit on a wafer. A large AI processor may allow only dozens. Lose one small chip, and almost nothing happens. Lose one enormous AI die, and hundreds or thousands of dollars in potential value can disappear from a tiny patch of silicon. That is why semiconductor manufacturing is not won simply by owning newer machines. It is won by learning how to operate the entire process with fewer defects than your competitors. Every production run generates data. Engineers adjust temperatures, exposure doses, chemical concentrations, timing, and hundreds of other variables. Gradually, yield improves. A process that begins as an expensive experiment becomes commercially viable, then highly profitable. This learning creates a brutal advantage for the market leader. The company with the most customer volume collects the most manufacturing data. More data improves yield. Better yield attracts more customers. More customers create even more data. The machines can be purchased, but years of process knowledge cannot be delivered on a cargo plane. TSMC's financial results show what happens when that flywheel works. In the fourth quarter of 2025, the company reported revenue of roughly $33.7 billion and a gross margin above 62%. Its operating margin was 54%. Those are extraordinary numbers for a company operating some of the most capital-intensive factories on Earth. But those margins do not mean every semiconductor factory is automatically profitable. Utilization matters almost as much as yield. A fab carries enormous fixed costs, whether it is busy or quiet. Equipment depreciates. Engineers still need salaries. Clean rooms remain filtered. Water systems keep running. Maintenance contracts continue. Interest on construction debt does not care whether customers placed enough orders. At high utilization, those costs are spread across more wafers. At low utilization, the cost assigned to every wafer rises. A fab running at 90% capacity can generate excellent returns. The same building at 50% utilization can bleed cash, even if every machine is functioning exactly as intended. This is the semiconductor cycle. When chips are scarce, prices rise, and manufacturers announce new factories. But fabs take years to build. By the time new capacity arrives, the shortage may be over. Too many factories begin producing simultaneously, supply exceeds demand, and prices collapse. Manufacturers cancel expansion plans just as demand begins recovering, which eventually creates the next shortage. Memory chips make this cycle especially violent because products from different manufacturers are relatively interchangeable. When demand is strong, memory producers make enormous profits. When supply gets ahead of demand, prices can fall below manufacturing cost. Perfectly functional factories continue operating because shutting down completely may be even more expensive, pushing more supply into an already weak market. Leading-edge foundries face another problem: obsolescence. A conventional factory may operate with similar equipment for decades. A leading-edge chip factory begins aging the moment production starts. Customers constantly want smaller transistors, better performance, and lower power consumption. Every new process generation requires new tools, modified facilities, and billions in additional investment. The factory does not necessarily become useless. Older production lines can continue manufacturing automotive, communications, and industrial chips, but customers paying premium prices for the newest technology move forward. If your process falls 1 or 2 generations behind, the most valuable orders may move to another manufacturer while you're still depreciating equipment purchased to win them. Intel demonstrates how painful that gap can become. For decades, it operated some of the world's most advanced semiconductor factories. Manufacturing delays allowed TSMC and other competitors to move ahead at critical moments. Fabless designers gained access to advanced production without owning factories, while Intel carried the costs of both chip design and manufacturing. Once leadership was lost, catching up required spending tens of billions, while competing against a foundry already producing huge volumes for multiple customers. There is also geographic risk. Advanced semiconductor manufacturing is heavily concentrated in East Asia, particularly Taiwan and South Korea. Taiwan's position matters because TSMC produces a dominant share of the world's most advanced logic chips. A major earthquake, blockade war, or prolonged infrastructure failure would not merely affect one company. It could interrupt the production of phones, servers, networking equipment, vehicles, and weapons across the global economy. Governments understand this, which is why semiconductor subsidies have become industrial policy. The United States Chips and Science Act authorized tens of billions of dollars in manufacturing incentives. Europe, Japan, South Korea, China, and other governments have launched their own support programs. They are not doing this because fabs are easy investments. They are doing it because private economics alone may not justify duplicating an extremely efficient Asian supply chain, while national security may justify paying for redundancy. For you, the new owner, subsidies can reduce construction costs, but they cannot manufacture a good chip. Government money can build the clean room and help purchase equipment. It cannot instantly create experienced engineers, a reliable supplier ecosystem, or competitive yield. A subsidized factory with poor execution is still an extremely expensive empty room. Now, let us calculate 2 outcomes. Scenario 1. You build a mature node fab for $5 billion. It manufactures automotive and industrial chips on proven processes. Demand is stable, equipment is less exotic, and yields are high. At strong utilization, the factory may generate several $billion in annual revenue with respectable margins. The technology is not glamorous, but customers may keep the same qualified chip in production for years, because redesigning and recertifying an automotive or medical system is expensive. This is the boring version of semiconductor manufacturing, and boring can be very profitable. Scenario 2. You spend $20 billion on a leading-edge fab. You buy EUV systems, hire thousands of workers, and target AI processors. If your process achieves competitive yield and major customers commit volume, the factory can generate enormous revenue. A single advanced AI chip can sell for thousands or tens of thousands of dollars after packaging into a finished accelerator. But if yield remains low, The economics collapse. If customers delay products, utilization falls. If a competitor reaches the next node first, premium orders move away. If export controls remove access to an important market, demand changes overnight. If one critical tool supplier cannot deliver, billions of dollars in surrounding equipment may sit underused. The difference between success and failure is not the factory. Both scenarios can use beautiful clean rooms, brilliant engineers, and some of the most advanced machines ever built. The difference is whether enough microscopic rectangles emerge without microscopic mistakes at the exact moment customers want them. That is the actual economics of owning a semiconductor factory. You spend billions before earning $1. You purchase machines available to only a handful of companies, operate them near the limits of physics, and compete through knowledge that cannot be copied from a manual. Your factory consumes electricity like a small city, purifies water beyond drinking standards, and produces objects too small to see clearly that can sell for more per gram than gold. Do it right, and you own the machine behind every other machine. Phones, cars, satellites, banks, weapons, data centers, and AI systems all wait for your wafers. Do it wrong, and you own a $20 billion clean room producing the most expensive pieces of broken silicon on Earth.